Okay, ready. Lab 9 is the Advanced Assembly Program Development. And we are going to do debugging. If you remember, we use code blocks as our debugger. But this time, our new debugger is called GDB. Okay? GDB is a new debugger. It's actually inside code blocks. Okay? It's actually the debugger inside code blocks. Code blocks is just a mess. Okay? What's actually running inside code blocks is GDB. Okay? And then we are going to learn about stack pointer, SP or R13. And we are going to integrate an assembly function into a C main program. We can combine C and assembly together to make the whole C program faster. Okay? And finally, we are going to learn more about virtual memory. Virtual memory will link to chapter 6. Okay? This concept is going to present to you in chapter 6. Virtual memory. Ready? Lab 9 is so difficult. Okay? That's what I can tell you. GDB or GNU Debugger is a utility software. Okay? System utility software. You have to apply this source code, okay, into lab9_1.s. Save it as lab9_1.s. And let me explain this program a little bit. Okay? It's a global main function. R0 equals 0. R1 equals 1. Okay? And then we are going to jump to where? This label name, continue loop. Continue loop, we jump here. Okay? And then we compare R0 with 9. Under what condition? Less than or equal. Okay? R0 less than or equal 9. If the condition is true, what happened? We jump here. So we add R0 with R1 and assign the result to R0. Okay? So we loop something like this for how many times? R0 start from 0. So it's going to be R0 going to be 0, 1, 2, right? All the way to 9. Okay? And when it becomes 10, what happened? When R0 becomes 10, what happened? It's going to continue. Okay? It's not going to loop. So this one is a do-while loop. See that? It's a do-while loop. Okay? And I want you to put this into a make file. Okay? So in a make file, of course, this is a tab, another tab, another tab. So we are going to assemble into lab9 _1.o, and we are going to link .o into the executable file. Name what? Lab9 _1, and then we are going to use lab9 _1 as a input to the GDB. Okay, so this is input to the GDB. GDB is our debugger. So when you call make debug is gonna jump here and look for lab9 _1.s. Okay, lab9 _1.s, and it's going to do what I just explained to you. Okay, and then the prompt. This is the prompt sign of GDB. Okay, in parentheses GDB, and you enter a list command. This is a command. Okay, and hit enter. You are going to see what? You are going to see the code in assembly. Okay, list means list the instructions. Okay, and find the position of compare R0 9. Compare R0 9, and put that line number. Okay, X. Let's line number X. Okay, find the line number X that has this instruction, and then set a breakpoint BX. Okay, so X is a line number. I don't tell you. Okay, it's an unknown until you use the list command. BX to set the breakpoint at what? Compare at CMP R what? R0 9. Then use the command run. Remember, when it runs, it will stop at the breakpoint, and now you will see the feedback. Okay, breakpoint number 1 at this continue loop at what line number? Okay, and tell me what X. Put X here. Okay, then use the command info R to show the values of R0, R1, R9, and put them here. Okay, we care about R0, R1, R9, SP, and PC, and CPSR. Okay, SP, LR, PC, and CPSR. Okay, so this is gonna be the label name. Okay, 0x means what? This column is hexadecimal. This column is decimal. Okay, there are two columns, hexadecimal values and decimal values. We are talking about Lab 9. Okay, Lab 9. Answer the following question. Why? Number one, describe the report on the screen. What each column means. Okay, and how is it different from the reader screen, your screen? Why are the numbers in the rightmost column negative? Why these columns contains negative number? This column. Okay? And then type GDB C, enter to continue, because we stop at the breakpoint. Now we want to continue the loop. Okay, and now it's going to stop at the breakpoint again. So type in GDB info R to record R0, R9, ... Okay, again. And now you can see the difference between the previous and the current R0. Okay, you can see R0 is going to be added by 1. Okay, and then item number 12, we can disassemble. What does it mean? Disassemble followed by the label underscore loop. What is disassemble? Okay, you will see what the meaning of disassemble. Okay, and you will get dump of assembler code for loop is going to correspond to the number may be different. Okay, but the instruction is the same. Add R0, R0, R1. Okay, if we go back to the original source code, underscore loop correspond to this instruction. Okay, they are actually on the same line, but for human it's easy to read like this, but in computer, in the machine, underscore loop colon add R0, R0, R1. They are on the same line. Okay? And loop will become address. Okay? Underscore loop will be the address inside the memory. Okay, address inside the memory. And now the this location correspond to underscore loop. Okay? And the number can be different. So don't worry if you don't get the exact number, exact same number. Okay? Then type GDB C. Okay, type in C to continue. To continue and finish the loop. Okay? Number 14. Type in x/10i main. x/10i main. What does it mean? It's going to display. Okay? Display the main function. Main function for 10 instructions. 10 means 10 instructions. In what format? In what format? I to display the values in memory in the in 10i means 10 instruction. Okay? 10i 10 instruction. Okay, so it's going to start from main plus 4, main plus 8. What does it mean? It's actually main plus 0, main plus 4. That means this instruction takes 4 bytes. Another instruction, 4 more bytes, and 4 more bytes, and 4 more bytes. Okay, main plus 4, main plus 8, and fill in the blanks. Fill in the blank for how many? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so totally 10 instructions. Totally 10 instructions. Okay, so you need to fill up the blanks. This blank as well. Okay, and you can see another label name, continue loop plus 0, continue loop plus 4. Okay. Answer the following questions. Fill in the blanks as I mentioned. Describe the displacement number. What is the displacement? Here. Plus 4, plus 8, plus 0. They are the displacement. Plus 0, plus 4, plus 8. Okay. And what is the arrow? The arrow. What is this? Arrow. Okay. What is the meaning of this arrow? I don't know. You can figure it out. Okay. And then step 15. GDB SI. What is the meaning of SI? S mean step. I means what? I instruction. Okay. Ni. What does it mean? Next. N means next. I means I instruction. Okay, Ni. Next I instruction. Step 17. GDB, IB. What is the meaning I and B? Okay, I means B means breakpoint first. I means info. Okay, info breakpoints. Show all the breakpoints. Okay, and what line, and the breakpoint already hit how many times. Okay, info breakpoint. Alright, step 18. Once your program finish the loops, then delete all the breakpoints and answer yes to confirm. Okay, then you can run again. This is wrong. You can continue to finish the program. Okay, and once it's done, you can see the output like this, and then you can quit GDB. Okay, you can quit GDB. Okay, GDB is so difficult. Okay, pay attention. Next is about stack pointer. As I mentioned, SP or R13. Okay, stack pointer. You can use push and pop, and also some fancy instruction like STM, store multiple, and LDM, load multiple. Okay, load multiple. And there are totally 4 combinations: LDM, IA, STM, IA. See that? LDM, IB, STM, IB. IA, I correspond to increment, A correspond to after, IB, increment, before. Okay, DA, D stand for decrement, A after. DB, LDM DB, STM DB. D stand for decrement, B before. Okay, so you have I or D, A or B. So multiply them together. You can have IA, IB, DA, and DB. Okay, 4 combinations. Okay. So we will use this instruction for what? For stack programming. Okay? Let's go to Lab9_2. Again, our main function R1 equals 1, R2 equals 2. This is our comment, another comment. That means it explains this line. Okay? Store R1 into SP plus minus 4. What does it mean? It means memory at SP minus 4 equals R1. Okay? And SP equals to SP minus 4. Remember, the stack grows downwards. Downwards means the address is lower every time. Okay? Remember, SP grows downwards. Downwards means the value of SP is lower. How to make it lower? Subtract. You subtract 4 because R1 takes 4 bytes. Okay? R1 needs 4 bytes. And the second one, same idea, memory at SP, subtract 4 equals R2. Okay? And then SP equal to SP minus 4. Cool? This notation is called write back. Okay? This notation. Pay attention to this exclamation mark. It's called write back. Okay? Write back here. The meaning is SP equals to SP subtract 4. Okay? Next, we can pop now. The earlier they were push. Now we can pop. How to pop? You can do LDR instruction. Okay? What is the meaning of this? R0 equals to memory address SP. Right? And then SP equals to SP plus 4. Okay, same idea. And now return. Okay, so make Lab9_2 into the make file. Add this into the make file. Remember a tab. And make run, and then echo to show R0. Okay? So what should it be? What should it be, Ja? You push R0, you push R1 first, and then you push R2. when you pop first, which one is pop first? R2 is pop first, and then R1 is last. Okay, so R1 was 1. So this should be, when you echo, this should be 1. Okay? Please double check. Please double check. Okay. Now, lab 9_3. Put the code, put this code. Okay, and now we are going to use stmdb. This is equivalent to push. Okay, so what is the meaning of this? It's going to be memory at sp equals to left to right. So it's going to push R4 first, and then it's going to push SP to be R5, but before that SP equals to SP minus 4. Okay, so SP equal to SP minus 4. Alright, because of this, right back. Now it's going to pop with LDMIA. LDMIA. And this time it's going to be right to left. Okay, so we'll push R4 first, and then pop and push R5 later. So when you pop, what is the order? R5 value will get into R2. R4 value will get into R1. Okay, and now you can check by adding R0 with R2. Okay, to be, you can add them together. Okay, and then BXLR return. Add this to the make file and make, and then run, and then echo. What should you get here? Alright, you can double check. The last, I'm not sure. The last example, the last item is C, calling an assembly function. Okay, a main C program calling an assembly function. Now you have to use make file. Okay, you have to use make file, make. Go to Lab9, launch code blocks, create a file name, create a project. Okay, oh, you have to use code blocks? I'm not sure. Yeah, use code blocks, sorry. Then enter main.c like this, and this add s is an assembly function. Okay, add s is an assembly function, and create and file name add s.s like this. Okay, and add it into Lab9 _4 project. Okay, Lab9 _4 project. Yes. Build and fix any bugs and explain why the function works correctly. Okay. It should be no problem. Exercise. What should we do? Yeah, I know. Debug Lab9 _1 number 1 and number 2. Okay, they are easy because you launch, listen to me, you launch 2 terminals under Lab9. Okay, directory under Lab9 directory, and launch GDB on both. Launch GDB on both and check the PC register values. Check the value of PC and compare to PC in step 1 and answer why they are the same. Okay, why they are the same. All right.